Okay, welcome to the today's class. Today's lab. Lab is what is the lab number? Lab number 8, right? Let us talk about the shift registers. Okay. Okay. So in the previous class, we have seen what do you mean by a register. Okay. Um, we have seen the register. We have already seen that the 4-bit shift 4-bit register. So just this 4-bit register is simply the parallel combination of just simply the storing the data, nothing else here, right? Okay, the parallel in, parallel out. Okay, so how we have done this one? Let me give you the block diagram, then we can go and explain a little bit later. Something. Okay. Okay, therefore let me take 4 times this one. Copy and paste. Yeah. Okay. So what do you mean by the parallel in, parallel out? Actually, see what is the block diagram of this 4-bit adder? Sorry, 4-bit register. The block diagram of the 4-bit register is something like this. We have a 4 data inputs. Okay, let me call this is called D. Okay, we will have 4-bit output that is called, for example, Q. Let me call Q. Okay, and this data will be stored here or it will be transparent based on the clock signal. Okay, but before going to the clock signal, we have to go and give the reset signal as well. Okay, first of all, we have to clear the content of all the flip flops. Then we have to apply the clock signal. Okay, then we have to apply the clock signal. So the question is that we can describe this one with the help of behavioral model very easily, right? It is similar to that of the D flip-flop. Okay, just we have increased the size to 4-bit size. Okay, it's simple and straightforward. Okay, and I changed in my requirement that we have to write it in the structural modeling. That means we should know about the what is the internal circuitry of this particular top level module. Okay, so for that I have taken 4 flip-flops. Okay, let me call here is what we call it is, let me call this flip flop 0. Okay, this is called flip flop 1. This is called flip flop 2. This is called flip flop 3. That means what is the MSB here? Sorry, LSB here is FF0 is LSB bit position. FF3 is MSB bit position, right? Okay. Now, as we know that we have already declared what is the D flip flop. Okay. So what we have defined the D flip flop, here is the D naught, here we have written Q naught. Okay. D1, Q1. This is D2, Q2. This is D3, Q3. Okay. So this kind of flip flop we have already written previously. That's what I am thinking. Okay. Let us take the clock of this. This is called the clock, right? Let me write the clock here. Okay. Now we are going to talk about the reset signal also. Okay. Let me write this is a reset signal. If you're not specifying anything, whether you have to write the behavioral or structural modeling, then you can go straight away go and write behavioral model. Very simple and straightforward. Otherwise, if based on the requirement, we have to write, right? This is a reset signal. Okay. So therefore, this is called RST. This is called clock. Those are the inputs. So this is the fundamental thing. Now we have to give the connection according to what type of register it is. If it is a parallel in, parallel out, we have to take parallel input data. So according to that notation, what should be this one? This is a D of 0. Okay. What you will get here? You will get Q of 0. Similarly, you will get here is D of 1. Q of 1. Next, this one is Q of, sorry, D of 2. Q of 2. D of 3. And Q of 3. Okay. So this is for the internal diagram for this one, right? So what are the different ways that we have written the program in the last class? Okay, so since it is a D flip-flop, we have written the behavioral, simple behavioral model. And okay, load signal also we have used. Okay, somehow we have to keep the load signal also. If the load signal is required, then what we have to do? What is the modification that we have to do it for if we introduce the load signal here? Of course, that's not for the primary understanding for us. Let us look at the behavioral model. So the structural modeling here, just I have used. Okay, I have already defined somewhere the D flip-flop, and I kept it here in this way. Okay, I did a mistake here actually. I something went wrong here. Okay, yes, this is wrong actually. Unfortunately, the formats and axes I have not written correctly. Okay, so what is the D flip-flop actually? Uh, what we have seen previously. Let me consider. Okay. Is this correct or wrong? Right or wrong? It is right from there. So because yeah, this is connected to this one. Actually, this is the D in of this one is connected to this one, right? Okay. Right. Good. Okay, this is how we have to connect this one. Okay, I'm not going to discuss about it. Okay, but very importantly, we are going to talk about this one. Okay, if you have any question on this one, please refer the previous lecture and get it done. The same thing we are going to use for the purpose of shifting. Okay. Okay. So what we would like to shift actually, shifting means that we would like to go for serial in, serial out. Okay, serial in and serial out. What is the block diagram for the serial in, serial out? As you can see here, we have only one serial in data, nothing else here, right? Okay, serial in and serial out. We have a clock signal, we have a reset signal. As I told you that it's a 4-bit serial in, serial out. By the way, how many number of clock pulses are required here to load the data? Single clock pulse is enough. The moment if you apply the clock signal, all the data will be loaded into the flip-flops. Okay, one flip-flop, one clock is required. But whereas here, how many clocks are required here? It needs 4 clock pulses. Okay, how do we know? Let us look at this. It's a 4-bit serial in, serial out. Now, what is the connection? What should be the connection? Okay, you can see the top level model having only one input, only one output, one clock signal, this one. So we have to connect this thing. Okay, therefore, here the input must be something. Okay, what should be the input? Okay, of course, you should say that serial in, serial out, fine. But where you are applying the serial in, where you are getting the serial output, that's the question, right? That's where you can apply. We apply the serial in at the left side, right side, rightmost position, and we'll get the output at the leftmost position. Therefore, this is having the 2 possibilities. One is serial, sorry, shift left operation, and the next one is called shift right operation. So that means here, what is the shift left operation? So here the LSB is actually SI, serial input data, and MSB actually serial out, right? So shift left operation, from right side to the left side we are moving. What about this one? What is the LSB? LSB here is serial out, MSB here is serial in. If this point is clear, okay? That means serial in, serial out has 2 possibilities, shift right and shift left. Okay, right. Good, so far so good. Okay, let us give the connection according to this one. I'm going to write the shift left operation. Okay, that means this input should not be here. This is also should not be here, and all these things. Okay, what should be the name of this one? Serial in data. It is a serial in data. Next, see, one point you have to remember here. Whenever you are writing the structural modeling, okay, we are using the same type of flip-flop, right? Same type of flip-flop. Therefore, it is not necessary, right, to denote something like this. Okay, so just it is the same flip-flop. D and Q. D is the input, Q is my output. Okay, that is what I have defined somewhere. I'm using this one here. Okay, therefore, I have already defined this is the flip-flop, this flip-flop one. Okay, no need to worry about this thing. Okay, all are D flip-flops of the same input and same output. Okay. Now this is the flip-flop 1, flip-flop 0, 1, 2, 3, right? So definitely for the serial in, serial out, we don't have any parallel out also. Okay, we don't need any kind of parallel out as well. Okay, just make the connection something like this. The output of the first flip-flop is connected to the input to the next flip-flop, and something like this. Something like this. Okay, this is what actually S4 serial out. Now let us write the Verilog program for this. Okay, both structural and behavioral. How behavioral model is changed at this point, right? Okay. Okay, let me write, keep heading, serial in, serial out, left shift register. Okay. Let's keep the module here. What is the, how can we start the module name? What is the module name? Let us give module, serial in, serial out, shift left operator, underscore, structural modeling. Okay, SM I'm writing. What are the inputs here? Serial in. First of all, let me write the RST, clock, serial in, SI, SO. Okay. Now, right. What are the inputs here? Inputs are RST, clock. What is the output? Output, sorry, SI is also there, right? Yeah, very good. We have an SI also. Next, output is S4. Output is S4. So since I'm writing in the structural modeling, I don't worry about the register data type, right? Okay. So what is the flip-flop that I have written there? Previously, I have written one flip-flop. Okay. So let me go and take that flip-flop somewhere in the memory elements. Okay. So consider this. Okay, RST is not there, right? In that one. Yes, here is RST is there, right? Okay, let me take this, copy this one. And paste at this one. Assuming that, okay, I have declared this one with the help of these particular variables. Please remember this way. Here instead of D and this thing, I would have written this way. Okay, D and Q. Please remember this way. The previous also I have written like this. Okay, so this is what the flip flop that I have written. So that's the reason why this is called D. This is called Q. Something like this I have written. Okay. Now, so we are going to write the formals and actuals method. Okay. Now, what is this Q of this one will be connected? Dot of RST of the flip-flop is connected to whom? RST of this one is RST is connected to RST only. It does not have any change. Okay, let me write here is also RST. So the clock is also clock. I did not change that one also. Clock of D flip-flop is connected to what? The single D flip-flop clock is connected to shift register clock. Okay, it is a shift register clock. Okay, the D flip-flop D is connected to serial in of 4-bit shift register. Okay, so therefore the D of this one is connected to whom? Is mapped to serial in. Agreed? Okay. Next, the single input, the D flip-flop Q of D flip-flop Q is connected to whom? I have not used any data here. Let me call this is called Q naught, for example. Okay. Okay. Some other name we will take instead of this. T of 0. Let me consider this is T of 1. This is called T of 2. Okay. That means that is a while internal to the circuit, right? Immediately, let me write the while What is the wire size? 2 down to 0 of t. Okay. So therefore, the dot q of this one is connected to whom? P of 0, right? P of 0. Okay. So look at this one. So the clock of the reset of this D flip flop, the already defined D flip flop is connected to the RST of the 4-bit register. The clock of this one is connected here also. Let me write inside of it. Okay, that's it is more clear. This is called RST. This is called clock. Okay, this is the RST. This is the clock. RST. So now this one you did not forget about this one, right? Clock. Okay. So therefore, uh, if you observe this one, the D of this one is connected to serial in data. The Q of this one is connected to this one. This is connected to this one. And this is also connected to this one. Okay. That means defined D flip flop variables are mapped to the 4-bit register variables. That's what it is done. As we know that why we are doing this kind of dot notation, formals and actors, because the position of the variables is not worried about it. That's the reason why. Okay. So let me take, this is the, what is the name of this flip flop? FF naught, right? This is called FF naught. Okay. Right. We have to take how many times? Another three times that I have to consider. Okay. So only change here is, here it's not the one. Okay, of course, these are not square brackets. Please remember that. It is a open and close parenthesis. Okay, it's not square brackets. Okay, next, this one is, what is the D of this one? P of 0, right? What is this one? P of 1. What should be this one? P of 2. Okay. What about here? Output of the first one is P of 1. Next to P of 2. This one is, what is this? S0. Right? Okay, that's, it's very as simple as that. If you run this program perfectly, all right, you will get everything. Okay. And this one. Uh, okay. After behavioral modeling, we'll write the test bed for it. Okay. All right. Next one is, okay, this is the straightforward, and all the connections we have given, write the structure modeling. Absolutely fine. It will give you the right answer. But yes, yeah, module instantiation is very important. I forgot to write this one. So you have to change this one. Otherwise, you won't get the RTL schematic. Okay, because that's wrong. Now, let us go and write the structural modeling. Okay. Sorry, behavioral model. OP. Okay, let me go and write this. The module, serial in, serial out, shift left operator underscore the behavioral modeling. I think somewhere you have to write it as a 4-bit. Okay, so 4-bit is better. Any question? Okay. Uh, 4 bit, something like this I've written. Here also, I would like to write the 4 bit. Okay. What are the inputs here? RST, clock, and serial in and serial out. Okay. Now inputs again. RST, clock, serial in. Output, serial out. Since I'm writing in the Verilog, since I'm writing this one in behavioral, I'm going to write in the register data type. Okay, right. So what is the logic here? Of course, we have tried the always block. Always at the rate of posage of receipt, posage of clock. Let's begin. How do we write? How can we write this one? Look at this diagram. Whenever there is a positive edge of the clock, if of course RST is there, definitely output, all outputs are, all the flip flops will be zeros. Okay, that's what we can write. Okay, let me write the first, that is the statement. Okay, if RST is true, if RST is true, what has to happen? All the flip flops must be zero. Is there any information related to the 4-bit information I have written here? Have you written any 4-bit information in this particular one? We have not defined anything about it, right? So therefore, what we have to do, first we have to select the internal voids of that one, internal variables. Okay. So therefore, internal variables for this one is, we have to write it as a register data type, which are 2 down to 0 of, for example, T. In the structural modeling, we have used the voids. Internal variables are called voids. In the behavioral modeling also, if the internal voids that are there, if you want to discuss anything about the internal voids, then you have to write it as a register data type. Am I right? Okay, right. So if RST is true, what you have to do? Then T is assigned with 3 bit of all zeros. Okay, 3 bit or 4 bit. Let me consider here is a 3 bit or 4 bit. Is the first T0 is 0, T1, and T2, T3. Okay, I think it is a 4 bit size. Okay, not 3 bit size, it's a 4 bit. Okay, let me take this a 4 bit size. Okay, I will tell you why it is a 4 bit size. Okay, okay, therefore T is actually 4 bit of all zeros. Now the moment the RST is available, all the flip flops are 0. If the RST is not there, else depending upon the clock signal, something has to happen, right? What happened, we have to write here. So for every positive edge of the clock, what has to happen? So this input is going as connected as output, and this input is connected as an it will be transparent here, and this value will go here, and this values go here, right? Right. So then how do we do this kind of approach? Okay. For example, if you write like this, let's begin, because the fourth statement I have to write, right? Okay. Let me start the begin here. For every positive edge of the clock, what has to happen? Begin, and here, let me write T of 0 is assigned with serial in data. Am I right? Andana, what is the output of this one? What is the T naught? For every positive edge of the clock, T naught is assigned with serial in data. It's simply D flip-flop, right? Okay. After completion of this one, what has to happen? T naught is connected or transparent. The T naught will be transferred as T1. Okay. Okay. Next, T of 1 is T of 0. Am I right? For every positive edge of the clock, this is what happened. For the first positive edge of the clock, this will happen. For the second positive edge of the clock, this will happen. And the third positive edge of the clock, something happened, right? Okay. If next to T of 2 is actually assigned with T of 1. Okay. Next, T of 3 is assigned with T of 2. What I'm doing here, you're not getting point or what? The T naught is connected to this one. T1 is connected to this one. T2 is connected to T3. Okay. This is called T of 3. But what is the T of 3 here now? T of 3 is connected to S of 0. Okay. So that's also we need to write at the bottom. You go and write that one. Now finally, S naught is actually T of 3. If this point is clear, for every positive edge of the clock, this is what to happen. Okay. Now finally, this is the ending of the else statement. So therefore, we have started the begin and we have ended in this way. Okay. So if you write this program and if you synthesize this program, you will get only single D flip-flop only. You will get only single D flip-flop, something like this you will get. Okay. If you try and I'll give you the time after some time. You please check that one. You will get only this information. Okay. The clock and reset. Okay. So this is actually 4-bit data, but you will not get the 4-bit register. In fact, you will get only single register. Sorry, single flip-flop. Why it is so? This is because we are using the blocking statements. We are using the blocking statements. What are the blocking statements here? Look at this one. The moment if you're using this equality operator, okay, this is called blocking assignment. This is called blocking assignment. What is the meaning of the blocking assignment? That means, so first, this particular statement is completely executed. Then only it will go to the next statement. Okay. So therefore, that means it's completely evaluated. Okay. That means this will be evaluated. Okay. There are the 2 points that we have to remember here. Okay. The moment if you write here, for example, for the sake of simplicity, for example, S is equal A XOR B, I have written here. Okay. 2 things it will be performed. What is the first thing that actually it will do? Evaluate and assign. The 2 things is happening in this particular statement. Whenever the moment if you're giving this particular statement, the simulation tool will do 2 things. One is called evaluation. The second one is called assignment. Okay. That means evaluation means what? A XOR B will be evaluated, calculated what is its value. Okay. The right hand side expression is evaluated based on the given inputs. The result of this one will be evaluated to, assigned to, yes. For example, if I give A is 1 and B is equal to 0, this is what the text input pattern I have given. Evaluation means what? So A XOR B, that means one exclusive OR with 0. Therefore, what is this value? It becomes, what is the value? 1. Exclusive OR gate, the two inputs are different, you will get 1. That is called evaluation. Once it is evaluated, it is assigned to a signal. Now this value is assigned to who? Some signal. Some is assigned with 1. Okay, there are the 2 parts there in this one. So therefore, so that is how what is happening here. This is actually, of course, we have SI is only a single variable. There is no expression here. But anyway, that is called SI is evaluated. And then that value is assigned to T of 0. Once this is completely done, evaluation assignment is done, then it will go to the second statement. That means, so without completing this particular statement, it cannot go to this particular one. Okay, therefore, this particular assignment is blocking the other statement to not to execute. Okay, this is not to execute. Unless otherwise the first statement is not evaluated and assigned, it cannot go to the another statement. That's the reason why this is called blocking assignment. Okay, so therefore, this is called a blocking assignment. Equal to stands for blocking inputs. Blocking assignment. Okay, this point is clear to everyone? Okay. Next. So therefore, because of this one, what is the simulation synthesize tool will realize? Not simulation tool. Synthesize tool will realize only one single bit resist, one single bit flip flop. But actually, our intention is 4 flip flops. Okay. Therefore, we have to go and modify this particular one with the non-blocking statement. Okay, that means by now you are able to understand what is the non-blocking assignment. Okay, what is the non-blocking assignment? Okay, this assignment cannot block the further statement to assignment. Okay, so what it is doing that first it will evaluate all the right hand expressions. Okay, in this blocking assignment, non-blocking assignment, non-blocking. All the RHS, look at this one, all RHS is evaluated, all is evaluated at the same time. Okay, all the right hand side expressions are evaluated at the same time. So let me give you one simple example, something like this. For example, S1 is equal to A XOR B. S2 is equal to A and B. S3 is equal to A or B. For example, something else I've given. Okay, so these things are evaluated at the same time. A and A XOR B, A and B, all these are evaluated at the same time. Okay. Okay, therefore, there is a specific place is there that will evaluate A XOR B. There is a specific place where they will evaluate A and B. And there is a specific place where it will evaluate it A or B. Okay, evaluation is done at the same time. At t is equal to 0 time, all these statements are evaluated at the same time. But assignment will be done based on the place where we have applied. Okay, that means according to the order that will be assigned. Okay, therefore, according to this discussion, first it will be all the right hand side things are evaluated, and because of this order, that will be assignment is done. Is this point is clear to everyone? So because of this one, now it will show you the internal structure of 4 bits. Because it is evaluated means that what? So the first statement is evaluated. What is the evaluation actually? T of 0 is actually SI. Okay. Therefore, it will take one flip-flop, okay? And it is taking the serial in data and it will provide the T of 0, okay? That is one flip-flop. It will take the second input, okay? Second data. So T of 1 is actually T of 0 assignment. So what is happening here? It will take another flip-flop parallelly, okay? And apply the input is T of 0 and it will produce T of 1. If this point is clear to everyone? A very confusing thing actually. It must be very, very clear now. So T of 1 stands for the input is T of 1 and this is T of 0. Sorry, T of 2. Next to T of 3 is assigned with T of 2. T of 3 is assigned with T of 2. We have four D flip-flops. Okay, based on the order, the values are assigned to the flip-flops. Okay, therefore, the synthesize tool will realize this one effectively. I hope the point is clear, right? Okay, so therefore, you understand the concept of blocking and non-blocking statement. So all the RHS are evaluated at the same time and assignment is done based on the order. Assignment is done based on the order. Order of the statements. Hopefully you got this point of blocking and non-blocking, right? Okay. Now the question is that we should not use the blocking and non-blocking statement at the same program. We should not use blocking assignment and non-blocking assignment at the same program. That's the reason why, okay, it is also possible to use the non-blocking statement here as well. Okay, please remember that we always use either the blocking statements or non-blocking statements. Okay, preferably we use the non-blocking statements for the sequential design. Normally we use non-blocking statements for the sequential circuits. Blocking statements for the combinational circuits. Okay, we talk about this point a little bit later whenever the time comes. For the time being, just you please remember this. Okay. Okay, right. This is the one way of writing the behavioral model. Is there any other way to write the behavioral model effectively? A very single line code that I want to write. What is the single line code that I want to write? Okay. I don't want to use this kind of things like this, but what I can do. So look at this one. So what we have done so far, okay, for the serial shift register, the simplest way. Simplest way. Look at this one. So we have taken the 4 flip-flops, right? Assume in this way. Flip-flop 1, flip-flop 2, flip-flop 3. Okay. So let me write the first outputs, for example. This is called the Q0, for example. This is called Q1. This is called Q2. This is called Q3. These are the outputs of the flip-flop. Okay. So what do you mean by the left shift operation? What is the left shift operation? This flip-flop is filled with serial in data, right? Am I right? This flip-flop, second flip-flop is filled with Q0. The third flip-flop is filled with Q1. Fourth flip-flop is filled with Q2. Am I right? That is how I have to do it. Okay. Now, what is the content of the flip-flop now? Now, the content of the flip-flop is something like this. Okay. So therefore, this is available here. This is available here. This is shifted here. So let me write this statement is something like this. For example, the Q of the present flip-flop is equal to concatenation of Q of 2 down to 0 with the SI. A simple statement I have written in this way. Huh? What about Q? Look at this one. The first position of the Q, what it is there in the first position? First position is serial in data, right? What is the second position? Q of 0. Third position is Q of 1. Fourth position is Q of 2. Therefore, Q2 to 0 is nothing but what? Q of 2 down to 0 can be written. Very simple and straightforward way that we can write. Okay. Shall we write this one in the main program? Let me copy this program and let us do this kind of how we can use this statement inside of it, right? This will be very, very helpful when we design the complex circuits. Okay. What is the change here? Okay, the same program only, but t is equal to 4 bit of 0 is same. Which one we need to modify? Else block that I want to modify. I want to modify the else block. Therefore, I don't want to use the this much lengthy else block, right? I can remove this portion and I'm going to write this one effectively. What is the statement here? Someone? Q or T? Q or T? It should be T. Actually, we are using the T here, right? So therefore, T is equal to what? Concatenation of T of 2 down to 0, comma, serial input data, right? Now, should we write? Yeah, same position only we have written. No, we should not interchange the position because as it is, we have to follow that one. What is the first position should be here? Therefore, T of 2 should become here. T of 1 has to come here. T of 0 has to come here. S of the serial in data. Okay. Right. This is how we need to do. Okay. So therefore, this is what actually the thing that we have to write. So this is how we have to write. Okay. But because we have a provision to combine these two things, or these three things also, we can combine, not a problem, by using the vector notation. Okay, that's what, instead of writing this one, I'm writing here is T of 2 down to 0, I have written here, and serial out. So both are equivalent actually, right? These two are equivalent. Okay, so but what the serial out is required, right? What about the serial out? Okay, so therefore serial out is actually assigned with T of, sorry, T3, right? T of, any question? Yes, tell me. T3? SO is assigned. It's a 4-bit data, right? It's a 4-bit data. Okay. That means whatever is left out, the bit is there, that left out, that I have actually. Either you want to take it, so if this is what you want. Okay, T of 2 we have taken. Actually, why we have not taken the T of 2? Actually, this is the position actually. Okay, that's not right. Okay. So these are the positions actually, right? These are the Q3 position, this is the Q2 position, this is the Q1 position, this is the unit position, right? Okay. Now we would like to take the Q0, Q3 is actually the information. What is the Q3 information? What is there in the Q3? Q3 is in the Q2, right? Yeah, Q2 we have capital, right? Correct. We can take in the Q2. Okay, because this is where actually this is the flip-flop position. In this flip-flop position, what information that is there? Qt information is there. That Qt information we have taken. Right. Good. Okay. So this is how. Yeah, T is also. It's not necessary to write the three down to 0. No, it should be 3 down to 0. It should be 3 down to 0. Right. This because these are the positions, right? So these are the positions you have to write. Right. T2 to serial out. No, it is not T2. Actually, it's already these things are there now. So as you can see here, okay, you want to write it T3, right? Yeah, it's not. We can write it there, right? But you can write T3 to S naught. Okay. Yeah, here it's not required actually. It's not required T3. That's the reason why 2 down to 0. Behavioral model I have written. Okay, behavioral model. Direct see what you want to write here. So T2. T2 is assigned to, this is also right one. We can reduce that problem. This is also possible to write T2. Okay. Now, so T naught will be go serial input data is come here. This one is come here. This one is come here, and this one is come to. Very good. That's what you can write. Serial outdated. Very good. T3 is not required. Okay. Uh, but here T3 is required or not? Here also let us check. 3 down to 0 is required. What about in this case? Position flip-flop ones, how the positions flip-flop one here? What we would like to do here. So we have what are the positions of these things? Outputs of output positions. Here is the T naught is one position. T1, yeah, Q naught, Q1, Q2, Q3, for example. All these three flip-flops are available. For all these flip-flops I am available, I am taking use of T naught, T1, T2. Okay, T3 is not required. Okay, how we can modify this code then? If suppose, okay, let me take this one and let me take here is also 2. Okay, okay. What is happening here? They are the three internal wires, right? They are the three internal wires. Okay. Therefore, for example, this is called Q naught. This is called output is the Q1. This output is Q2. This output is Q3. Okay. So for the time being, what information that is there here? Q naught information is only there. Q1 information only there. Q2 and Q3. Okay. Now, if I'm shifting operation I'm doing here, SI will come here, Q naught will come here, Q1 will come here, Q2 will come here. Okay. For example, right shift operation I'm doing. That means starting from the leftmost position to the rightmost position. How it should be? This should be SI is here. This is called Q3, Q2. This is called Q1. Therefore, definitely 4 positions are required. 4 internal positions are required for it. Okay. Yeah. Okay, so this is what we normally write it. 3 positions. Because that tells us that the 4 flip-flops having the 4 outputs. T is equal to 0 stands, T is equal to 3 down to 0 stands for, we have a 4 flip-flops having the 4 outputs. 4 input, 4 outputs we have got here. Okay, so this is how we can write it. Okay, this is the first flip-flop. Okay, let me write here only. Okay, here. Okay, here you can see this is the one output. Okay, this is the second output, third output, fourth output. The 4 outputs. Okay, so therefore this 4 outputs information will be transparent. Okay, in everywhere. Because otherwise if you're not writing this one, what will happen? S naught is only single bit information. Okay, you're not able to do this kind of thing. Okay, at the later part we can see that the S of 0 is actually we'll take the T of 2. What is that? Error file. Ah, no, it doesn't matter. Okay, I don't. Okay, because already I have mentioned the T3 here, right? Okay, T3 information is I have written here. Okay, T is assigned. Value is assigned. If you're not assigning any value, then it is saying that okay, it's undetermined. Even if you not assign something, it is unknown value will be shown there. But luckily that I have written here is unknown value there. Sorry, 0 value I have mentioned there. Okay. Right. Now let us go and write the test bench for it. Right. What is the test bench for it? Okay. Let's write a module. SI serial in, serial out, shift left operator, 4-bit underscore behavioral model underscore test. Okay. Oh my God. Okay, what is the next one? Register data type, RST, clock, serial in data, next void, SO. Let me start the clock and R clock. Let me write the clock. Okay, not clock. Initial block. Let me write initial begin. What is the RST first of all? RST is equal to 0 and clock is also 0 and serial in is also 0 at 0 nanoseconds time. Okay. Madhutna. Next, after for example 1 nanosecond, let me write 1 nanosecond. Let me keep RST is equal to 1. RST is equal to 1 and serial in data is clock. I will do it later because it's a periodic signal, right? Okay, but just initialize and later I'm going to change something. Serial in data is equal to 1. Okay. Okay. So let me end this one. SI is 1. Okay. Let me take the serial in data, but let us change the serial in data also. Okay. Another 1 nanoseconds. That means 2 nanoseconds. Or maybe, for example, 5 nanoseconds. Let me write the 5 nanoseconds. At 5 nanoseconds. So not 6 nanoseconds. Serial in data. Reset is 1 means it is okay, as long as reset is equal to and the output is equal to 0, right? Okay, let me keep one thing. Let us take the initially this is 1 and later it will become 0. Okay, because RST is 1 and 0 okay. Okay, therefore serial in data is equal to 0 at this point. Okay, another 5 nanoseconds. Serial in data is equal to 1, for example. Something like this I am giving. Okay, about the serial in data. Let me end this particular one. Okay, next time go and write always block for the clock signal. Always for every 5 nanoseconds, clock is equal not of clock. For every 5 nanoseconds, the clock is equal not of clock. When we can stop the simulation? For example, 4 clock pulses, that will be 0, right? So that will come to the all the serial in data will be transferred to the serial output side. Okay, the 4 clock pulses are required. Okay, that means how much this value is. For example, 50, let us give. Okay, 50. Okay, it's more actually. Let us look at that one. Okay, we can stop the simulation at 50 nanoseconds. Initial at 50 nanoseconds. Dollar stop. Okay, of course, before going to this dollar stop, let me, what we have to write? Block we have to write, that instantiation, right? What is the instantiation here? Serial in, serial out, shift left, 4-bit underscore behavioral model. Okay, this is called M naught. What is this one? RST, clock, serial in, and serial out. Okay, so this is what after this one I'm going to stop my simulation and finally end the block. Okay. So what kind of output that we will see? Let's draw this one. Well, let's draw the output waveform or the expected output waveform. What I have written first of all, I've written the clock signal, right? 1. If the clock signal is equal to 0, and after 5 nanoseconds, this will be high, and another 5 nanoseconds, it will be low. Okay. Another 5 nanoseconds, it will be high. Another 5 nanoseconds, it will be low. Another 5 nanoseconds, it will be high. And another 5 nanoseconds, it will be low. It's the high, sorry, low, high. 15, 20, 25, 30, 35, 40, and then 45, 45, 50. This is what the signal is. Did you catch this point? This is the clock signal. What I have written, what about the next one? The RST is equal to 0 at 0 nanoseconds of time. That means at 0 nanoseconds of time, the RST is 1, sorry, 0 now. 1. It is 1. How long it is 1? Till 1 nanosecond. For example, let me consider this is 1. Till 1 nanoseconds, this is 1. After that, this is 0. Are you getting this point? And this is forever 0. But we stop the simulation at what? 50 nanoseconds. So till 50 nanoseconds, this is 0. Did you catch this point? Okay, therefore, this is what I have written. RST is equal to 0 at 1 nanosecond. Okay, at 0 nanoseconds, this is 1. At 1 nanoseconds, RST is 0. Therefore, at 1 nanoseconds, this is till 1 nanoseconds, it is 1. At 1 nanosecond onwards, it will be 0. Right. This is called RST. Next, what is the next one? Serial in data we have to write. What is the serial in data? First, initially, that is 0. Okay, that is initially, this is 0. Let me take, this is the color. Okay. This is 0. Initially, this is 0. Okay, next, what it has to be? When this is high, therefore, at 1 nanoseconds, it becomes high. Okay. Till 1 nanoseconds is 0. And this becomes high. Next, it becomes 1 till 5 nanoseconds. Another 5 nanoseconds. That means till 6 nanoseconds, it becomes 1. This is the 6 nanoseconds. Okay. Okay, this is the 6 nanoseconds. 6 nanoseconds, it becomes 1. At 6 nanoseconds, it becomes 0. Okay. At 6 nanoseconds, it becomes 0. Right. Right. Okay. Next, what it has to do? Another add 5 nanoseconds. That means at 11 nanoseconds, it becomes 1. 11 nanoseconds. So let's go to the 11 nanoseconds till this point. 1. And this is 1 forever. Till, because if I'm not writing anything, if I'm not changing anything, it will be remains there. Okay. That's what I have written in my test bench. What I'm expecting my output. This is called serial in data. What is my expected output? Okay. So intentionally, I have used the flip flop is equal to the reset is 1. Okay. Intentionally. Why? Because I want to make the flip flops contents are 0. Therefore, intermediate signals, right? These are the intermediate signals. This is actually 3 down to 0, right? This is actually 0. Okay. Usually the intermediate signals will be written in this way. This is all are zeros. Okay, till this point. Now at 1 nanosecond, okay, what is happening here? So at 1 nanosecond, so do we see any kind of clock signal? There is no clock signal. Till the clock signal, what it has to be? What it has to be? Same value, okay? The same value only. That means it is also 0, 0, 0, 0 only. All are zeros only. What is the output for this one? What is the serial out? What is the serial out? 0. Okay, because we have mentioned that this output is 0. Okay, that is 0 till this point. Okay. Clock edge is positive here, right? Clock edge is positive. There is no reset here. Okay, fine. Now the what is the input here? The input is 1. That means that is shifted to whom? T1 position. Okay. Therefore, what is happening here? Till the next positive edge of the clock. Till the next positive edge of the clock. This value will be so what is the LSB position? LSB position is 1. This is 0, 0, 0. The internal flip flops are 0, 0, 0, 1. Okay. Now what is the output here again? What is the serial out? How it becomes 1? Because we have written the code is actually this one has to go as an output, right? Okay. So therefore, this is a serial input data. First flip flop LSB position. This is the MSB position. MSB position is actually your output, right? So this is also 0. This is also till this point, this is 0. Right? What is the next one? At the and next another positive edge of the clock. Again, you can see there is no RST, but there is a 1 is there. Therefore, what is happening here? Till the next positive edge of the clock. That means till the next positive edge of the clock, this is go something like this. Because this is the bus representation, okay? Nothing else here, right? It is a bus representation. Okay, so what is this value? 0, 0, 1. It should be 1, right? This is the 1, right? At this point, this is the 1. So therefore, the 1 is again, will go insert into this one. Okay. So what is the output here now? 0 again here. The serial output is also 0. Here also 0. Here also 0. What about this one? Okay, next to positive edge of the clock, all right? 0, 1, 1, 1. Okay. What about here again? 0 only. Next positive edge, till this next positive edge, what about this value? 1, 1, 1, 1. So now this is now, look at this one. S out is equal to now becomes 1. Now this becomes 1. And I stop the simulation at 50. I stop the simulation at 50 means that again, this value will go something like this. Okay, to the next positive edge of the clock. This becomes, again, it is 1, 1, 1 only. Okay, now this is again. So therefore, this is what we can see. Therefore, this is 0, this is 1, this is 1. Right? That is what the expected output you have to get. And you have to verify in your rewarder tool. Okay. So therefore, any program that you can change, okay, whether this you take this one or maybe you can take the this one, it doesn't matter. Okay. So it will produce the same output in this way only. You have to verify that one. Okay. Now, in the same scenario, is it possible to write the shift right operator, shift right operation? Okay, please try to do it as a format. Okay, and completed the shift right operation. And because of the lack of time, you are not able to complete the very essential thing. But anyway, no problem. This is enough. Please try to in your home. Please try to write the shift right operator and also write the bidirectional shift register. Bidirectional shift register. Okay. If you're not able to do this one, I will complete the bidirectional shift register in the next lab, as well as the universal shift register and linear feedback shift register. They're the three important registers that are there. I will discuss that point later. Okay. We stop here today.